Okay, hello everyone. Good morning. Thank you for joining this session. My name is Kogan. I am a European test manager at Hardware Analytics and Test EU at Synopsys. Welcome aboard. Today I'm going to talk about testing and monitoring silicon throughout the entire life cycle while leveraging existing high-speed functional serial interfaces. So with that, let's see what it's all about. Okay. This is the agenda we have for today. I'm going to talk about the advanced silicon test challenges. I'm going to talk about our solution, defective-parts-per-million and Silicon Max HSAT IP, and an overview on that. Different configurations that we offer, a bit about the software and EDA automation, and I'm going to also mention some key partners that we have and the reference design for this solution. So with that, let's deep dive into it. So then test challenges, what are they in this new era of advanced silicon? So obviously scale complexity. So design sizes keep growing, the transistor density keep rising, there is the manufacturing variability, and there are other challenges as well. There is the packaging evolution, there's the system complexity, and workload increase. Everything is happening at the same time. Now, we're used to talk about the Moore's law, and that's fine, but we came to notice that in order to adhere to this rising complexity in all arenas, we actually need to talk about something we call at Synopsys Sys-Moore, which is actually more than Moore's law, as you can see here. Now, some say that the packaging evolution going to 3D-IC, packaging chiplets will give the answer to that, to this challenge, but probably it is a combination. Probably we have to do many, many things in order to really adhere to the challenge. Now, today I'm going to talk about one of the things we can do, which is speed up the test, and let's see how that can be done. So why is there even a problem? So you can see here that number of patterns in the test world keep rising in as far as the technologies keep shrinking. Typical number of patterns that you need in order to achieve your test goals, test coverage goals keep rising, and that's money at the end of the day. Money that you have to pay for this test time. Now, number of flops keeps growing. Typical flop count in millions keeps growing according to the different usages of the SoCs. And then the demand for product lifecycle debug, whether it's in automotive use cases or whether it's in, let's say, in cloud use cases for servers. Again, this is a big challenge for us. Now, what do we do about all that? So one solution might be to leverage from the fact that we do have high-speed channels available on most of the SoCs today, whether it's USB or PCIe, which are capable of carrying bandwidth which is very high. And usually, of course, it's utilized for functional reasons, but a revolutionary idea would be to use that bandwidth for test purposes. Now, that can happen either in production mode, or it can even happen, or might even happen in field. And we'll talk about that along the way. So, when we talk about that, actually, so we call this idea high-speed I/O, HSIO-based test. Now, how would that look like? So one option is to actually use the functional protocol, whether it's USB or PCIe. In theory, it could be others as well, for this solution, right? That means you have to get your scan data into packets and get them into the SoC and use them inside the SoC for test, and then ship out the packets as well in order to compare the expected data to the real data that is provided from the SoC. Now, there are other solutions as well being discussed. So an alternative for that would be to use the same functional file which is there, the service file that is there, in order to in order to actually run the 1149.10 new standard, IEEE, of course, running on that PHY, and I'll show a diagram for that as well. And that is very good for manufacturing tests, maybe less for in-field. And then there could be, in theory, a test-dedicated PHY that you put on your system, on your SoC, for that purpose. It might have some benefits, but today this solution is more theoretical. Okay, so what is the solution that I'm mentioning here? It's actually a combination of the TestMax ALE software that we have and the IP, the Silicon Max HSAT high-speed access and test IP. So let's talk about that for a second. So again, let's assume you have your tester here, and through that, you drive the functional interfaces of your USB or PCIe into the SoC, and data is written through your AXI bus into the IP, which actually translates that into scan data, driving at the end those internal scan chains that you still have, right? So the revolutionary idea here is not to use the GPIOs or whatever digital ports you want to use usually for your scan chains, but instead the functional interface. Now, that might have a lot of advantages, because suddenly the limit that many SoCs have on the numbers of ports that they have in the system is gone. Now, that limit is usually a hard limit, and that has a direct effect on the number of scan channels you can use for each macro, in case you have hierarchical design. And in turn, that would have a great effect on your test time, because it would affect your the length of the chains that you use in or channels that you use in your system, and then it would affect your length of the shift, of course, which dominates the patterns. So all of that translates into the number of channels you might have at your system, which is a great benefit. While doing so and utilizing this solution, so you also need the software for that, obviously, and that comes from the TestMax ALE part, which is part of the Synopsys TestMax family of test products that I show here. And all of that can actually be used in the context also of adaptive learning. So on top of that, adaptive learning could be utilized in order to optimize the performance of that test. So again, the combination, how would it look like? Remember, the purpose here is to test the dies. So you need the testers to support that, and I'll show that later. But I can actually utilize this combination in order to test your parts, whether those are packaged dies that you test in production, whether those are already in the field dies that you want to do in-field tests on. All this becomes possible suddenly for many purposes, many different usages, right? I mean, for example, one could think of a way to even update your scan patterns in a much more efficient way through the functional interfaces, and if needed, allow to run this test in field on your dies, on your parts, using the updated test data. So all of this is a big advantage. Okay, so let's look a bit at this diagram and see what kind of parts does this solution have, right? So as I mentioned, it would have the PHY. We're looking now at the DUT. So it would have the PHY of the USB or PCIe, and obviously the controller as well. So all this is the functional serial interface part you're all familiar with. Now, that would probably write to some AXI fabric that you might have on your SoC. And in turn, this would actually communicate with the HSAT IP. Now, that is the part that is able to translate the packets, or here it's actually data already, into your scan data, right? Allowing you to feed your regular scan network that is there on the chip, possibly your tap controller using probably 1149.1. You might have whatever it is, 1687 network, 1500, doesn't really matter. You use your own scan network, the regular test network that you have, while applying this solution. So the idea here is that there is a distinction between the functional part, which is the high-speed interface, and the test part on the right-hand side. Both are the same ones you would have in a regular system, only now you have also this IP translating. Of course, it works as a bidirectional translator because the data that you compare to also needs to come out of the SoC in the form of packets. Now here we see the entire system. So you can see that the tester might even have a driver in case of production, for example, use case. So we'll talk about the way you generate the test patterns and what kind of transformation you have to do to them through the TestMax software. But then this data gets driven by the tester through the high-speed interface, whether it's USB or PCIe, into the DUT, as I showed you before. And then the same translation goes again here between the HSAT IP and the test network. So all of this is actually done here from the tester to your DUT. Now, another possible configuration that I'm showing here, again, this is the DUT part, would be to use the same functional PHY that I mentioned before, only this time without using the functional protocol. So what does it mean? It means that data is no longer translated into data packets of your functional interface, but rather your functional PHY actually runs the 1149.1 protocol. So the only addition you need the only addition here to the system is actually the HSTAP controller, the high-speed tap controller, which is able to communicate on one side with the functional PHY, and on the other side, it is actually talking to the regular IP that I showed you earlier. So here, that's the only additional part. Well, when you compare it to the previous and maybe more classic solution of HSIO. Okay, so what kind of automation do we need to build around this IP? So imagine you have your RTL and then you want to test it, right? So you have your scan network, the regular one that you want to have, but then you need to add this IP that I showed you in the previous slide. So you write out that IP. You need to configure it. You need to generate it. Always an IP comes with constraints, timing constraints, and those have to be adhered. You integrate that IP. You can validate it. You get a test bench, which dynamically allows you to validate your whole system. And you get, as part of it, you also have the AXI loopback test that checks it on, even on that level, everything performs fine. Now, all of that is performed through our TestMax Manager platform. And many of our customers know that already. Now, with that, it is supported also to work with a third-party tool. As I mentioned earlier, if there is a total disconnect between the functional interface that is used and the scan network, then we can actually insert the relevant IP, configure it again, generate it again, even create a test bench. But then at this point, a third-party tool takes over and is responsible for the scan data itself. Now, of course, the scan data still needs to be translated into the right protocol that is chosen in the solution. And all of that is supported. But the generation here in this second approach, the generation of the scan data, whether it is, for example, style format or any other format that is generated, all of this is the third-party DFT tool is responsible for that. And we do support that. So the test max here is still generating the IP, configuring it, connecting it, and that's it. Here it stops. Of course, the first option, the full solution in that sense is much more robust, and the way you can validate it gives you higher confidence in the system in that sense. Okay, so let's talk a bit about the software. How does it really work? So you run your ATPG tool and you create your ATPG patterns. Now here usually, next thing you would do is take those patterns, let's say to your ATE, and that might be through some format conversion. Sometimes you would use our defective-parts-per-million tool, or you might have another solution to convert your patterns into the tester format. Now, in this solution, the next step would be to run testmax.ale here, which is actually the one that is translating the test data into the world of packets, packetized data, or high-speed, using the high-speed data interface that you chose. So with that, you get your HSAT patterns, and you can run simulation on them in that format. And once you have those and you simulated them, you can actually perform your handoff to the ATE. This time, instead of in the regular tester format, in the format of the high-speed data. And then you inject it to the DUT as I showed before, using the high-speed interface, translated the data is written to the IP as before, and then to the scan network. Now, that's obviously not the end of the story. And why is that? Because we also need to be able to debug and sometimes find diagnosis, whether it's because parts are failing, whether because there is some systematic failure that we'd like to debug. Patterns might have issues, all sorts of reasons, of course. So we must have this capability. So the way it goes is that we do reverse mapping from the data that is there, that is running on the tester in this packetized format. We are deriving the packet compare, the failure at the packet level. And again, through the use of testmax.ale, we actually transfer it to your usual cycle failure, and pin and cycle failure actually, which tells you which pin is failing and in which cycle. Now, this transformation is crucial in order to run your regular diagnosis. Of course, you cannot run your diagnosis directly on the packetized data. You have first to do this reverse mapping here on the right side, get the scan data that is applied on the chip, and then run diagnosis on it. So all of this is fully verified, and we tested many times, and also in our system with customers already, and so working quite well. So you can rest assured that while enjoying the benefits of this new system, utilizing the high-speed interfaces for test purposes, you still get the you still get to enjoy all the diagnostics capabilities, so you don't lose them in that sense. And this is very important for all our customers. Okay, so some key partners here, and I mentioned testers before. So this is very important that a tester would be able to actually understand this format, use this data in the different high-speed interfaces that we support. So one example here is Advantest. There are some details here, but actually they show you that the new testers support this format, and you can give them data coming out of TestMax ALE directly in the packetized format, and they will be able to understand it, work with it. So this is very important to have them as a partner supporting this, but they are not the only partner that we have. We have also Teledyne here, showing again their solution. Again, fully supporting our software of TestMax ALE. So this is obviously a new capability that is built into the new testers. So customers using those testers could enjoy this capability and benefit from it. You're more than welcome, by the way, to approach them. Both of them, Advantest and Teledyne, they'll be more than happy to share with you this data, and more than that, and any success stories they already have with this. Okay, and to conclude, we also have here some reference designs that we can share with our customers. So we have those for PCIe, whether it's XDMA or DMA. We have also a USB reference design. So you can see here in the picture, this is what it looks like. It's using some example that we have on an FPGA. So it does show the conversion that I was talking about between the functional interface and the scan interface. So this is very nice. I mean, for customers who would like to consider adopting this system, we really recommend making good use of this reference design, because it really shows you how it works in the real world, not just on the slides or in simulation. Okay, so with that, we're almost at the top of the time that we have today. What did we see here again? To conclude, we saw a revolutionary way to inject test data into the SoC, which can be used in production mode, but also in field. In production mode, again, it would be used by for the tester, and I showed the partners that we have on that, and in field, which is sometimes equally important. In some cases, like automotive use cases, might be even more important. You would actually use the functional drivers that are there. So you could imagine even that software which is downloaded from the cloud could have some test data inside it, and that might be used in field in order to test your part. And that could be even updated software, right? So it means that the time you have to develop your scan data is actually longer. And the time it takes you to inject the data and check it, all the tests is actually running much faster. So you enjoy a lot of benefits here. Imagine after some time in the field, parts tend to have some issues that you did not encounter to begin with, and you did not cover somehow in your original test. Then you get a chance to update your test, which is something that could be crucial, and you don't get every day a chance to do that. Now, as test engineers, we are fully aware of the fact that usually we get maybe a chance to update our test data in production. Even that is not that simple to do, but here you get a chance to do it in field as well. So that was it. I was Tal Kogan from Synopsys, and I'll be happy to take any questions you might have. Feel free to approach, feel free to send me an email, kogan@synopsys.com. I'll be more than happy to take your questions. Thank you very much for your time. Enjoy the rest of your day.